Hello friends, welcome to the next lecture in the series Thermal History of the Universe. So in this lecture we are going to look at the number density of particles in the early universe. If a particle has chemical potential mu, then the chemical potential of the corresponding antiparticle is minus mu. We will denote the number density of particles with n and that of the corresponding antiparticles with n bar. Now let us prove these results in the relativistic regime. Number density of particles and antiparticles is given by this expression. And for fermions, if we take the difference between particles and antiparticle number density by keeping mu chemical potential terms, we get the exact expression. In this case, in the part A, we are ignoring chemical potential in the relativistic regime. But when we take the difference for fermions, for the particles and antiparticles, difference between the particles and antiparticle number densities, we get the exact expression. We will look at it. And in the non-relativistic regime, we get these two expressions for number density of particles, number density of antiparticles, and the difference between the two number densities. Okay, let's see how we can derive these expressions. For relativistic species, temperature is much greater than mass, and temperature is much greater than the chemical potential. And we have seen in our previous lectures that the distribution function is given by this formula, by this expression, and there is no mu term, so mu is the same for n, same for n bar, and number density n will be same as number density of n bar, will be same as number density of antiparticles when we ignore mu in the expression. So when we ignore mu in the expression, we can write number density n is equal to number density n bar is equal to this. And you can see that the integral is pretty straightforward. 0 to infinity, sorry, this is not 0 to infinity, but you are integrating over all possible p-values. And once you convert this dqp to 4 pi p square dp, then integral is from 0 to infinity. And positive sign is for fermions, negative sign is for bosons. I set up two integrals, and positive for fermions, negative for bosons. Number density of fermions is given by this, number density of bosons is given by this, and we simplify these two integrals, these two expressions, and we get this result in Mathematica. So you see that the number density if I factor out g t cube zeta by 3 pi square, I get 3 by 4 for fermions, and I get 1 for bosons. Okay, so that's the expression for number density of particles, which is same as the number density of antiparticles in the non-relativistic regime. Now we will calculate the difference in the number densities without ignoring a chemical potential. We will keep the chemical potential term, and this is for fermions. For fermions, we can see that for fermions, we get the exact expression. For fermions, we get the following expression. And how do we do that? Again, pretty straightforward in Mathematica. Set up the two integrals, one with the mu, and for n we have e minus mu. For n bar, we flip the sign of mu and subtract 2. And I tried to Google to see if any textbook has solved this integral. And I saw that this textbook, I can show you maybe somewhere on the internet. You see that in this textbook, after a lot of digging in the internet, I saw that this textbook has solved these integrals, or maybe I don't know if there is a proper solution, a full solution, or they just provided some hints here. But you may want to look at this textbook and see if you can find analytical solution. But I used the power of Mathematica, and I will show you that even in Mathematica, you have to do some tricks in order to get this exact expression. So first of all, the integral for particles is this. Then integral for antiparticles is this. I solve these two integrals. Then I assuming that temperature is greater than 0, because otherwise it gives me this conditional expression. So I would simplify the difference between these two integrals, assuming temperature greater than 0, and I get this. Then I want to expand this expression, and let's see that after expansion what do we get. And by the way, here is an example of how expansion works in Mathematica. If I do series expansion of, for example, I'm demonstrating you how to do series expansion in Mathematica. This is an example. If I do series expansion of sine x and x around 0, and then I want to keep first 7 terms, then you can see that when I run this, I get this first 7 terms. And then if I change it to 9, then you get first 9 terms. If I change it to 10, you get first 10 terms, or maybe if I change it to 20, you get first 20 terms, like this. See, you get first 20 terms. Now, so what I'm trying to do here is what am I trying to do here? 1 second. Yeah, so we have in our scenario, mu by t is approximately equal to 0. So let's expand mu by t around x. Let's substitute mu by t equals to x and then expand around x equal to 0. So in the previous expression, which is this expression, see, this is what I get for the difference between the integral. This is what I got, and I would substitute mu by t to x, and then I get this. And then I would do series expansion, and I would keep first 10 terms. And this is what I get after series expansion. So you see that only 2 terms are surviving, even when I get the first 10 terms. And I have tried expanding up to 100 terms, but always 2 terms survive. Then I do call this function normal, which will give me the non-zero terms. I mean, it will remove this term, and I get finally this thing. So when I do series expansion, I think this normal is not required, because I have seen that only x to the power 3 survives, up to x to the power 3 survives. So I do I need this normal? Maybe not. Let me run this without calling this normal. Okay. So if I don't call this normal, Mathematica would return this last unnecessary term. which I don't need this order x to the power 4. But if I call with normal, then I don't get that last not required term. So this is the exact expression which I get after after we do expansion of this expression. This is the difference between integrals, and after doing series expansion, this is what I get. So now finally I multiply this by g over 2 pi whole cube into 4 pi into integral difference 4, and x goes to mu by t. I would simplify, and when I simplify, I get this. Now from this I would like to factor out gt cube by 6 pi square. So I have written one custom function in order to factor gt cube by 6 pi square. So I have, this is my custom function which I have written, and then I call that custom function, and I say to that custom function that from this expression please factor out this, and it returns me in this form. So gt cube by 6 pi square factors out, and inside the brackets I get this, and this is what I want. A particle number, the net particle number, or the net particle number density, I think. What is it called? Let's see. It is called yeah, the Fermion occupation number. Yeah, so the net particle number density is given by this expression. Now next is that what do we get for the non-relativistic species? For the non-relativistic species, again, we have seen, we first of all write the formula for number density. Then we have seen that Fp in non-relativistic regime can be written in this form by like energy can be written in this form, this, and then you can write this p square plus m square in this form in the non-relativistic regime, and finally Fp becomes this, and the number density expression is pretty straightforward calculation here up to this point. And then this integral, again I would use the power of Mathematica to solve this integral, and I get this. Then I multiply by the required terms, and finally I get this. So this is our number density for particles in the non-relativistic regime. For the antiparticles, you flip the sign of mu, and you will get this expression. Now the difference between the number densities of particles and antiparticles is given by like you subtract the two, subtract this minus this, and then you get this after you factor out this part, and then this is sine mu by t. So 2 sine mu by t. So you write 2 sine mu by t here, and then you finally get the difference in the number densities in the non-relativistic regime. This is non-relativistic regime. This is in the non-relativistic limit. Okay, so in this lecture we have proved these expressions for the number densities. In the next lecture, we will look at the expressions for the energy densities. Thank you for watching this video. Please share your comments and suggestions for improvements. Thank you. Take care. Bye-bye.